Good afternoon, everyone. Good afternoon to those who are in the room and to those who are watching us remotely. Today we have a final intern project of Anderson Avila, who is PhD student in Institut National de la Recherche Scientifique.
Very good.
In Canada, under the supervision of Dr. Tiago Folk. And today he's going to talk about his intern project, audio quality assessment with deep neural networks. Without further ado, Anderson, you have the floor.
Thank you, Ivan, for this nice introduction. Thank you, all of you, for watching my presentation. This is the outline of my presentation. Start with a little introduction on audio quality assessment. Then we dedicate some time to explain our data set, which took a massive amount of time to develop, and it's a really nice data set. Then we discuss our proposed approach for the problem of audio quality assessment, and then the results and the conclusion. So what is audio quality assessment? So the idea of the audio quality assessment is to estimate the quality of the audio based not just on the signal attributes such as SNR, noise level, speech level, or reverberation, but also considering the human factor, the human subjectiveness. So at the end, we want a model that can give us a number that will represent the quality. And why this is important, so many multimedia services, network systems, they need to be monitored. And we cannot just look at the quality of the service without considering or taking into consideration the user, the end user. What we could do was to have a feedback from the end user to monitor our service, but this is not always happen. So an alternative is to have a model that can tell us how good is our service, also considering the perspective of the user. So at the end, we don't want to, for example, in a voice call and a VoIP, the user having problems of not hearing each other or not being able to synchronize the conversation. So all these things can be monitored and improved if you have a feedback from the user. So these are some of the possible examples of network impairments that can hinder a call or can compromise the quality of the audio. So latency, jitter, packet loss. And on the signal side, you can have like speech distortion, such as additive noise, reverberation, clipping. So all these kind of artifacts can hinder communication based on audio. So how we can actually assess the quality of the audio? We have two alternatives. One of them is to have people assessing the audio files. So we can have a speech being recorded and people can listen to it, and then each participant can give a score. Then you get what is called MOS. So the MOS is just the mean or the average of all these scores. And this is important because it eliminates the subjectiveness of each individual. So each person has their own reference of quality. It depends on many different aspects. For example, if the person is an expert, they might be more rigid. If the call or the audio, the content is important, might also influence the score. So with the MOS, we can eliminate these factors. So the subjective listening test is actually the most reliable one, but it has some drawbacks. So it's time-consuming, it's laborious, it's expensive, and I think one of the things that is really complicated is that it cannot be done in real time. So if you have a model that can do this for you, you can actually evaluate your systems on the fly. So another alternative to subjective listening test is to compute MOS using an algorithm. So we replace the human by a computer-based algorithm. We have two types of algorithms. It can be signal-based. So the algorithm looks at the signal and extracts some attributes or parameters of the signal to estimate the quality. We have a parametric-based, which is use network parameters to estimate the quality, and we can have a hybrid one. So we can use the signal without reference, right, to estimate the quality, or we can use a double-ended one, which uses the reference. So we have the degraded signal, the clean signal, and then you compare the two. That's what PASC does. We're going to talk about this metric in a little bit. So these are some of the mostly known metrics or measures for audio quality assessment. We have PASC, a new version with can be used for wideband signals, Polka. So these are all developed by the ITU organization. And you can see that, for example, PASC is more, was trained for codecs and compressions, not really for noise and reverberation, other kind of impairments that you can have in the signal. So you actually have some limitations. So therefore, this is actually the motivation for our project. So although PASC is widely used, it has some drawback. It was not really trained for distortions introduced by the speech, actually trained for distortion introduced in the speech compression, but it is intrusive. So it needs the clean speech or reference speech to compute the output. So our objective is to have a new algorithm that can be trained on noise, reverberation, audio, pipeline distortions, and also that is not intrusive. So these are the two main things that we are looking for. When you look at the literature review, we are actually, in this project, we are focusing more on deep learning approach to build our model. When you look at the literature review, we see that there is a lot of work on using deep learning for predicting mostly intelligibility, and but not really for speech quality in general. And most of these approaches are based on a speech recognition, so they actually estimate the quality considering the performance of the speech recognition systems. There are two approaches that I thought was...
Also, it's visible that most of the papers are from this year.
Yeah,
except one. So it's a kind of a new thing in the community.
Yeah, those are papers that recent papers. They are focused on deep learning to solve this problem, but most of them focus on intelligibility. And intelligibility is actually just one factor or one aspect of quality. So this paper I thought was interesting, although it's also focused on intelligibility. But the idea here is to have a spectrogram of your speech signal and then use a CNN and their kernels as a filter to estimate the MOS. It actually eliminates some of the engineering features that we know by using a CNN as a filter and as a kernel. This one was also a paper that I thought was interesting. Is an end-to-end non-intrusive speech quality assessment model, and it uses a spectrogram and a LSTM to estimate the quality. So I thought it was interesting that they built actually their own cost function. They customized it, and to get the correlation between each samples or the sequence of samples here, they estimate the quality by frame. So usually what we have is the overall quality for the whole utterance. And in this paper, they actually were able to explore this information to estimate the quality of by frame and then get the overall quality. So now, talk about the data generation. So we had spent quite a few time to try to generate a more realistic data set with different impairments. We had initially a clean speech, 2,000 files. Then we convolved it with different impulse response to simulate reverberation, distant talk. We had the reverberant speech samples, then added noise. We had like four categories of noise and with different SNR. and also different speech levels and noise levels. We're going to show all the statistics on the data in a few slides. So at the end, we had like 10,000 noise samples. And to train our model, we divide it this way. So I want to now talk a little bit about how we labeled the data. Before I just...
One question from previous slide. Upper right corner, start line, random noise level at 50 dB SPL, standard deviation of 0 dB, or it's a type?
Yeah, it's a typo.
Okay.
So it should be 10 dBs.
Okay.
Okay, so this is just a model how the quality is perceived by the humans. They actually are divided in 3 events. The first event is the physical event, is the waveform reaching out the ears. We perceive the sound, then we have the perceptual event, where we actually extracted the features such as loudness, noisiness, reverberation. So we automatically extract those information from the audio and compare with the desired features. So the desired features is the internal reference that each person has, and then we can make a judgment. So after doing the judgment, we are able to estimate the quality ourselves, and then maybe have a description of what effect was played a role on the estimation of quality. So basically, this is what will happen when we have people rating our speech file, our samples.
B, J, D, and D on the block in the boxes.
Oh, this is the perception. It's a judgment. This is the description. So we have the perception of the physical event, which is the waveforms. We measure the features internally. So that's the perceptual event. We compare them with the desired feature, which is your internal reference. Then you can make a judgment. How good is the quality? So the thing is that people have different desired features, right? So we have different expectations. And then we do the description. So the idea of the MOS is to minimize or mitigate this.
They two outputs, they look the same. They have the same description of quality features. How are they different from the two?
I believe here is the. So here is like considering the desired features with reference, and here is just considering the degraded signal. So here it would be like a non-intrusive, and here intrusive because you have reference.
I see.
So I thought it was important to, before talking about our listening test or our listening quality test, to make clear what are the effects that people are listening to. So we have like the reverberant speech with RT60 ranging from 300 milliseconds to 500 milliseconds, and in our discussion was the most common range. And we have close talk and anechoic speech. So in terms of SNR, this is basically the range of SNR. We're gonna check the distribution of SNR in a few slides. So we have also noise and speech level varying. So all these variables actually are being assessed by people.
Sorry, quick question. So the SNR changes has a huge range, but your reverb doesn't have a huge range. Why is that?
Well, those are the RT60 that we had at hand. I think one of the things that we discussed is these are the most common type of RT6 that we can find in rooms like such an office or in-house. So maybe higher than this would...
From your office to this one?
Okay. I mean, there's some, like a treated office will be 200 or 100 even. And then my living room is 1,000. So why not go from 100 to 1,000?
Yeah, I think this...
Because you're going from 0 to 40 dB SNR. So that's a pretty good range.
Yeah.
I'm just curious.
because this is the impulse responses we have. And you guys gave us.
And also we had like the Skype pipeline, which apply enhancement to all these impairments. And actually we divide the data set between 50% with using the Skype pipeline and 50% not using it. And we see like there's an improvement, slight improvement using the Skype pipeline.
What does it include, the Skype pipeline?
Is the ACG,
Noise suppression and ADC.
yeah, and also the enhancement. So actually this is what
And
people,
we have actually, Ross, some non-convoluted speech signals, which means zero.
Yeah, it's close talk is 0.
Yep.
So you do have 0 in there.
yeah, yes.
So when you do the AGC, what is the output of this? I mean, is there like a SNR range was adjusted, or what happened after the output of the Skype pipeline? Was it within a...
Well, when you look at the distribution of the MOS, at least, you see a slight improvement. It's not huge, but it's actually doing something in terms of enhancing the signal.
So if you don't do the AGC, I would assume the signal would saturate in some of these sounds would saturate and the MOS would suffer because of that. I mean, what is the reason of doing the AGC? Why do you need that?
To analyze the performance of noise suppression and ADC.
No, hold on.
With and
Step
without.
back, Chandan. We need AGC because somebody can be at 1 meter, somebody can be at 4 meters. This is 4 times difference in the level of the audio, of the speech signal, and you need to equalize it before to send it to the other party. That's the first thing. We did not do normalization when you compute the RMS of the entire file and eventually multiply it, simply because AGC introduces its own distortion. So the gain goes up and down based on what it thinks when we have speech or not. And we wanted those distortions to be implanted into the signal, so to get users to judge how much irritating is this or not.
And did that affect the MOS? I wonder. Like he says there was some change in the MOS, like how, like...
It does. From time to time, actually, it's annoying. But
Right.
in most of the
It
cases,
is.
it's seamless.
Yeah, so ADC had a big impact, more than noise suppression.
I see.
But it was an improvement.
AGC was an improvement, but noise suppression was actually degrading the
Right.
noise.
So in general, AGC with the voice activity detector works nice, works quite well. If the VAD misfires and you have a noise signal and it considered it as a voice, it starts to run the noise floor, and that does not sound well. Or if somebody speaks from far away and the VAD does not fire, then the voice still stays weak, and this also is not very pleasant.
But in the realistic case, the AGC is still there, right? In the real case, when people are really using
This
Skype.
is processed with the Skype pipeline.
Yeah.
The code which is in production, I think. Right, Chandan?
Yes.
Okay, so this is what coming to the participants. So for each condition, we had 10 participants, so we average over 10, and then we get the subjective scores. So we're not just getting the scores, but we're also asking the participants to evaluate each one of these effects. Then we're going to see how they relate to MOS.
And so, these effects can be on or off. And
They're always on. So you have like mixed effects here. You don't have like exclusive effects.
Okay.
So this is actually the UHIS, which is the outsourced company that provides human resource for us to do this kind of experiment. So people, the first thing that they do, they read the guideline, they go through a training where they get familiarized with each one of the impairments, noise, reverberation, etc. Then they go to a qualification part where they go through the experiment, and then we use a gold standard file, so we know what to expect from their ratings. So after that, they go to the test itself. So they listen to the file. After that, these buttons are enabled, so they can rate from 1 to 5. And then we ask them which device they're using and also which impairment was mostly disturbing. This is a little bit of the data exploratory analysis. This is our MOS, and this is a PASC, and this is the SNR. The SNR is supposed to be like a normal, so we actually added a little bit more low SNR, so we get the MOS to shift a little bit to the lower values. And the reason is because we want our model to actually learn how to rate also this kind of situation. But people were kind of generous when they were rating. Well, I was thinking that because people were not using our service, they were like working for us, so they tend to be, I think that may play a fact. So
did people give a real actual number for that mass, or you derived that number?
we have to derive it because remember we need to average over 10 people or even more to eliminate the subjectiveness or the individual factor.
So 9 question, okay. So why are they unrelated? I mean, aren't they supposed to be correlated? PESC and mass?
So PESC is pretty bad.
Oh, PASC.
So that means PESC is bad?
Well, PASC, but the way I see is that PASC, you see it more correlated, more close to the SNR distribution. You look at only at the signal. PASC doesn't really look at the subjectiveness of the.
It's supposed to look, right?
I don't think it was trained for this.
It's not trained for this.
It's trained only to evaluate the distortions caused by speech compression. That was the initial idea behind. So you have codecs with different bitrate, different codecs algorithms, which means predominantly relatively clean signal from a phone or closed-top microphone. You compress it, and then you decompress it, and you have to judge the quality.
So
This is why even the traces of noise make PESC to give you a low score, because this thinks that the codec introduces those huge noises there.
I don't know, Ivan, because we have plotted PESC and POCA, remember, like in our they were quite reasonably correlated.
So you'll see PESC and MOS from the judges have 0.7 correlation. Their correlation, you see the same trend, it's just the absolute value. PESC is more strict and gives lower score when you see noise. If this noise is natural, humans are more forgiving.
And we use this for our speech enhancement
Yes,
evaluation, so it's
I can write a book
pessimistic.
chapter why PESC is bad, but we don't have anything better than that. So this is the better thing.
Okay.
Yeah, just this point about the MOS, I think if people were using our service, they would be more strict with the MOS. I think the fact that they are kind of getting paid to do this, they might be more generous. That's one assumption.
So did you compare this with expert ratings?
No.
Okay.
Okay, so a little bit more about the data. So here we have MOS and SNR, and you see that so MOS tends to be correlated with the SNR. So I'm not saying that it's the cause for the SNR, but it plays some effect on the SNR. So the noise level, it seems like when the noise level gets higher, people tend to give a lower MOS, but it's still like lower is still like 3, right? That's why you get the shift MOS distribution. For me, the way I see this is people are more concerned with the speech, if they really can hear it. So if the noise is tolerable, they don't really care much.
So wait a minute, what is this? These are all 10 numbers and this is the average?
Yeah. So yeah, exactly.
Doesn't look like
No, this is actually the MOS. The MOS is already
No, what is that line and what are those dots?
the line is like the correlation between the two.
The trend.
Yeah.
So that,
How they vary together.
I think so here you have interactions, right, between the impairments, so correlation doesn't make.
Yeah, of course. Like I mean, just to have an idea. So it's not here is not just the SNR that is. That's why I showed this slide here, so people know that these things are on all the time. So we cannot really just analyze SNR and say that's the only
Go
effect.
back to that figure.
Yeah, so each dot should be a file, right?
Each dot should be a file. Yes, that's right.
And so each file gets rated 10 times. and then the value in loss should be the average of that, right?
Yeah, yeah.
I see.
Okay.
This is
And
why
then-
you have every 10th.
Yeah, and then the curve should just be the mean of that.
Uh-huh.
And what is that? What is that thing around the curve that?
Should be a confidence interval, right?
But Anderson, in general, noise level per se is not indicative because under the same noise level, if you have a louder or softer speech signal, you'll get different results. SNR is more indicative, and you see that it is actually
Yeah,
more.
yeah. But I was curious to see how these two things plays out, considering, you know, because these things are changing together, right? We don't have fixed speech or noise, so these are all effects on the outcome.
So Ivan's comment might not hold if you look at the middle and the third picture.
What's that?
Noise level and speech level.
Yeah, I think the fact that you actually see a correlation, like of course there are interactions, but you cannot deny that there is a correlation between.
In
there's an
general,
effect
yes.
of, so the speech level doesn't mean any more than the noise level, but the fact that they're delivered at the same absolute playback level, it shows that, okay, if you crank up the noise, it doesn't really matter as long as the speech level is okay.
Yeah, that's the
But
point.
I don't see that in the third picture. I would expect the third picture to be the same or similar to the middle one. No?
No, because imagine you have noise here, but you don't really care, right? Because you are being able to understand or listen.
Okay.
So that's why as the speech level increases, MOS is increased. So you have a better level of speech. So it's more comfortable for the listener.
Yeah,
And I
again,
think you saw that, Chandan, right? And I think one of your comments was that that's why you were saying like let's lower the speech level because that's what people are getting bothered with
Yeah.
to get the lower MOS.
Yeah. Lower volumes had the biggest impact on the MOS.
Yeah.
so I'm just still concerned about that distribution here. The dots are distributed all over. It looks like they're all over the place, right? For example,
Yeah, there's a lot of variability because you know they have other things going on here. It's not you cannot just say, oh, this is noise in MOS. No, we have
That's why it's difficult to estimate it.
there's a lot of interaction here. We have all these
It's like
things
random,
playing.
right?
But we'll see.
Even with the same SNR, you can have problems in the networks properly simulated with a lot of dropped packages.
No, but this is
which-
ground truth, not even network. This is ground truth
No,
result.
those are the files.
I know, but people have annotated them and we have computed the mean, right? So the annotation
Yes.
seems to be at noise level 40. Let's say the MOS is.
Let's say you have a file at 20 dB SNR, but this file, they can be distortions from the speech enhancement, distortions from the EGC. They simulated, Skype team simulated the network, they may be packages dropping in certain files which brings the quality down. So I think the bottom line here is that there are way more factors impacting the
Than this
perception
does.
of the quality than the SNR, which is quite frequently used in scientific papers as the quality measure.
Yeah, I mean the point here is just to say there is some trend in the data, and we can actually extract some information, but we cannot say like this is causality between speech level and MOS. And here, this is also I think interesting. So this is actually what people reported as more disturbing. So and then actually when they reported noise was more disturbing. Noise was actually increasing in terms of disturbance, we have a decrease in MOS. So that's what people thought. So before was the ground truth, right? And here with reverb, so as Ross said, maybe we should have, there's a trend here, but this, the X,
The x-axis.
this noise, but this is what people said.
What are the units?
If we have 3 judges of 10 clicking on there is noise in the file, you'll get to 0.3.
Is this thing?
See it? Because each judgment, there is a noise in the file is with resolution of 1/10. Because you have 10 judges, 3 clicked on it, it's 0.3 noise level.
No, but Ivan, isn't this the wrong way to plot it? Because X-axis should be the only thing varying, everything else should remain the same. For every point here, to understand the trend, if you want to study the trend between mass and
That's
noise.
in the science way, but this is kind of more practical thing. You have 10,000 files with
I understand.
combinations of everything in there.
I understand, but this is, I mean, you cannot infer
But
from
the-
this
but
graph
the
saying noise and mass.
Still, you can say that when pretty much everybody hears the noise in the file, this means you lost 1.5 points of mass.
No, there are other factors at play, not just the.
That's fine. You try to basically eliminate them by averaging. This is the trend line.
Yeah, I think the problem, I think we can do that kind of exploration. We just would need more time. We get the data ready.
If I were to do this, I would keep everything the same, just change the noise level and get the.
Yeah, but we don't have that in our data. That's the thing. The way our data was generated, we have mixed effects in the data. That's what people are hearing. What we can do is, when plotting it, we can maybe get the SNR with one range,
Yeah.
and then get the other. But the SNR is random, so even within that range, we're going to have some variability.
Actually, if you just took all the files that were people only clicked noise, what does that plot look like?
But
So the
Only
single
click noise,
pair-
but that's the thing, we don't have that. Because people have the option to that's, you see, this is not it's not exclusive, so you can hear noise, and because that's what is in the file. Noise, reverberation have mixed effects.
But what if you keep only the files without no reverberation and no anything else?
That's
Or-
possible,
or
because you
low?
have,
So I did that analysis. So people who chose only noise as the problem token analyzed the mass. The lower volume token had the highest impact on the mass, more than an impact on mass.
So we still have to do some data mining here.
Also, I guess the question you're asking here is for people to tell you what you already know. You put the noise in there, you put the reverb in there, you're just asking people how well are you able to correlate your own judgment to what the condition was. But in the end, you probably don't care about whether people thought there was too much reverb, you care whether people, or I don't know, I guess that.
yeah.
But
Because-
what
because,
we see
I think
here is that actually unnatural speech hurts most the perception of the quality. You see, you can lose up to 2 points for unnatural. Reverb is less than a point. Yes, at some point, more and more people click on reverb, but they don't punish it that much. And noise is somewhere in between.
Which might just be an indication that reverb might matter, but it's not something people think about when they give a low score.
Maybe.
And that's again, there's the ground truth. You know how much reverb there was, so you can actually eliminate that.
Or maybe it's just less annoying for humans.
Or you didn't put in 1,000 milliseconds.
That's true. That 500 milliseconds is here.
Right, this is okay, this is treated.
Yes,
So-
which is pretty much a normal environment, so they don't get much annoyed by that distortion.
Okay, so now let's go to the proposed approach. The first approach that we thought was using iVector. So the iVector has been widely used for recognition tasks. So that was one of the motivations. So has been used for speaker verification, language recognition, emotion recognition. And the question was, what about speech quality? So can you use iVector for that? And iVectors, they are known to carry speaker and also channel variability. And the way you can think about the iVector is you extract several observations from your speech file, usually MFCCs. And the bottom line is, so you want to map those features into a utterance level vector, which is the iVector. So we want to map them in this total variability space. So the way we do that is, first you compute a GMM-UVM model. So this background model will have a bunch of speech files, and it's going to be like a reference or like a mean in this space here. After computing the GMM-UVM, you extract some statistics from each one of your observations here. So you get what is called the supervector. So the supervector is composed by the components of your GMM and the features length that you have in your feature extraction. So this supervector here is what you are going to use to compute the I vector. So M here means independent supervector, which comes from the GMM. And we have the dependent supervector. So the dependent supervector depends on your speech file. So every new speech file, you are going to compute like the offset from the GMM UBM, which is kind of your mean I vector. To do that, you have also to compute the low-rank total variability matrix, which is the T matrix, and we use the UBM and the Baum-Welch statistics to do that. So this is the framework for the I vector. After preparing this framework, we extract the I vector for each utterance in the training set, in the dev set, and in the test set. So here are some plots of the I vector projecting the clean speech, which is the dark blue dots here, and MOS below 0.5. So you see that it projects the I vector and can actually separate the two sets. So here's considering MOS between 2 and 3. And when we consider actually the whole, the 3 levels of MOS with the clean speech, we see that the data get a little bit mixed up. There's some clustering here, but there's some limitations. So then we thought maybe you can use I vectors combined with a DNN, MLP architecture to find a better representation to compute MOS. So this is the architecture that we propose. Like we have I vectors of 400 dimensions. We have the 2 hidden layers, 200 hidden units first layer. The second layer we used dropout as regularization and ReLU as activation function. And then we predict the MOS with this model. So the second approach was using what is called the key CEPSTRAL coefficients. And again, it's has been used in basically in speaker verification to detect natural and unnatural speech, and has been very successful in that. So that was one of the motivations. And the other one is that it's psychoacoustic motivated. So the idea of the constant key CEPSTRAL coefficient is they say that this Q or the quality factor increases as the center frequency increases. So as you go up, this factor will increase because the window length that you extract your samples, they are fixed. So what they propose is to make this Q factor constant and change this so that this doesn't change. So the motivation for that is that we're going to get a spectrum. There is or better resolution for high frequencies and low frequencies. So that's how it would look like. So you'd have this kind of spectrum using their model, the CQT. So this is how it's computed. So you compute the spectrum, but using the Q transform, the Pauli spectrum, the log. And this is actually a spectral feature. So they use they have to change the scale, the log scale, and they do that by using this uniform, and then they compute the CEPSTRAL. We use 2 approaches for these features. The first one using CEPSTRAL, and the second one using the spectrum. And so the idea here was, okay, so if you remove the signal process computation of the spectrum. We know that CEPSTRAL features are very well established. But if you let the DNN look at directly on the spectrum, would you get better results? That was actually the question here. Okay, so this is our evaluation. We use evaluation setup, so we use the Pearson correlation and the mean square error to compare the models. As baseline, we use MOS, and we compare also our results with SRMR, P563, and PESC. So SRMR is also a metric, a measure for estimating reverberation, and we want to see if they can also be able to estimate the quality for the impairments that we had. And P563 is another metric, is a non-intrusive metric. There is.
What is this P563? Is this ITUT recommendation?
Yeah, it's ITUT.
Okay, it's ITUT recommendation P.563.
Mm-hmm.
Okay.
So all the results are based on the test sets.
So you didn't use POCA?
No, we tried, but we didn't get rid of it. We didn't get a graph of it, but you know.
You didn't get what?
We didn't have the code for that.
I had it. You should have asked.
Oh really? Oh my god. Okay.
He slept 2 hours last night. He probably ran
There's no
some
time.
test.
So maybe next summer. Okay, so this is the results for the I vector. And actually it's pretty similar to the results we get with the CNN on the CEPSTRAL coefficients using the Q constant. And one thing I was thinking here is that, so I vector is projecting CEPSTRAL features or MSCCs to the total variability space, and the CNN is basically doing the same thing here. So that may explain why the results are very close. So this was a bit surprising for me. So actually, like removing one signal process computation, we get better results just looking at the spectrum. And then we have PESC to compare with the SRMR and P563. We also explored, with the help of David and Hannes, another architecture using MEL features in a full connect MLP, and we got a pretty good results here. So the other thing that we explored was using this same architecture here, which is computing the MOS on a ultra-dense level, but using on the frame level here.
Yes.
Okay, so what we did was to compute here we use all the features here on the frame level as an input for an ELM and extract some statistics from the ELM to get the results. So what we found is that the ELM actually helps to decrease the variability of the data from 0.22 to 0.17.
And how you get the results per file, because the fully connected network gets a segment of the data. In this case, so you have a segment, you move and get a certain number of variable length estimations. How you compute them here for the entire file? For ELM, I know how. This is our standard engine.
For the utterance, we just take all the frames that were in that utterance, and that's what's passed to the. We get the statistics on that, and that gets passed to the ELM.
Here, yes, I know, but here,
And that's also that's the per utterance results.
how you get the number for the uterus here?
The
Average? What do you do?
it was just the correlation. It's just
No, he's telling you get a correlation per frame. How do you
just like all
Per segment.
frame.
So you have this network running on a segment of 25 frames.
from
Yeah.
there?
And then next,
Right.
and you have a bunch of numbers which is with variable length. How you compute the number for per uterus? Here.
That was the result. We just looked at all the frames that were in the utterance.
Uh-huh.
Yeah, 25 frames. 25 actual
Uh-huh.
physical frames.
Segment by
Five
segment?
segments, whatever. So each of those what we call the 1450 vector frame. Each of those frames, we just looked at the core, what was the result, what was the loss estimation on that, and we just looked at the correlation over all, across all those frames.
All
So it's
of
like the
them.
utterance level before the ELM, and then the utterance level after the ELM.
So pretty much this is one solution. This just
Yeah.
tells us how much ELM
That's just showing how much the ELM
Okay.
improves it.
Okay.
But and everything's utterance based up above, so that's also utterance based.
So pretty much the last line is your standard workhorse neural network for doing whatever we do with audio.
Mhm.
So, naive question, what
Impressive.
is MSE computed between?
Sorry?
MSE is computed between what two things?
Oh yeah, the two, the ground truth, which is the MOS, and the NR predictions.
MOS is one number, right?
Yep.
And
Oh yeah, but you have,
What is
okay,
mean
in the test set, you have, in my case, 1500.
mean square error over all the.
Yeah.
905.
Yeah. So EML is like,
So you are underestimating by 0.17, basically.
No.
Best estimation.
This is just a Pearson correlation.
No, MSE. So the error in estimation is about 0.2, meaning if the PESC is 2.5 or MOS is 2.5, this is estimating 2.7 to 2.3.
Roughly, yes.
That's what it means.
Yep. Anderson, do we have an estimation of how well humans do?
yeah, no,
Humans mean square error.
yeah. Well, we should get the data
No,
a couple
you
of
have
days
the data.
ago.
No, you have the data, right? People
Yeah, yeah,
For the
it's,
same file, people have given 10 numbers.
yeah, that's
Compute
right.
this range for those
Yep.
10 people.
And
Yeah.
I would love to have one more line. Humans.
Variance, yeah.
So the standard deviation is
Oh,
typically
okay.
1 point.
Yeah, one.
It was around 0.7. Okay.
So technically, 10 people, if you average 10 people, get around 0.3 mean square error. Square of 10 times less. So technically, this means that if you get a 0.17 or 0.16, you are as good as 50-ish people doing most tests.
If it scales linearly. But nobody knows that. It's empirical.
Still not bad.
What was the difference again of the second and third models?
Okay, so this one is looking at the CEPSTRAL. So you compute the spectrum, and then you compute the CEPSTRAL, and then use the CNN. So this one is just the spectrum, yeah.
So you let the network figure out.
That's right, yeah.
Okay.
That's right. So we, just to conclude, we developed a new audio quality data set with labeled, and I think it's very realistic data set. I think we can explore a lot of things on this data. We explore also the effects of mixed impairments on MOS. We explore 3 approaches to estimate MOS, and we show that our methods outperform all the baseline methods. So as the next step, so we want to investigate maybe the combination of I vectors with CEPSTRAL features, see if we can get better results. We definitely need to test our algorithms in new data sets, and we want to explore more neural network architectures, end-to-end DNN. So we want to explore a little bit more the DNN plus EML and CNN plus EML. And so I'd like to say special thank you for the Skype team. So Shandan was a great help, Ross as well. Great discussions. I learned a lot in this internship. I'd like to thank you, all the people that supported, funded, Johannes and Scott, Hannes Gumper, Dave Johnson, so you helped a lot also with your technical expertise. It was really nice to have you guys. And the whole audio and acoustic research group, especially Ivan, was really nice, was always there when I needed. And it was a great time for me.
Questions? It was actually quite nice discussion during the talk, but if you have more questions, please
I have a
ask.
comment. I think one of the main
And
things,
comments, sure.
yeah, one of the main things to do in this is actually to do what Johannes was suggesting, right? Is to get expert opinion on this. Because people are giving some mark scores, but it might just be random, right? I don't know how reliable they are because these people are just people,
Yeah.
right?
Yeah.
But isn't that the point, though?
No, you also want to get an expert opinion to see.
What is an expert opinion? I play a sound file that has five different distortions, and yeah, you can say, based on my expert opinion, I think there's 500 milliseconds reverb. That might actually impair your judgment because now you're basing your judgment based on what you hear in the file, not what you might perceive when you have an actual phone call with your.
That is fair,
Wow.
but it's at least going to give you a metric to say how much is the variance around. Basically, if the 10 people marking the mask score varies from 0 to 1 to 5, then it's just noise, right? I mean,
Well, you said it was 1 point standard deviation between.
Oh, typically in MOS, Skype MOS scales, our variance, our standard deviation is 1.
yeah.
Right. So it's not.
But here, I don't know how much was the standard,
Yeah,
nobody knows, right? So the standard deviation is about 5 here, right? Then it's useless.
Yeah.
Right?
I think
that-
It's
think,
like 7.7 for this.
0.7?
Yeah.
Okay.
So the reason I was suggesting getting experts to check some of the ratings is it looks like you have a central bias. So things are kind of centered around 3 to 4 rather than spread out. If you ask a bunch of experts, they shouldn't have this bias.
Yeah.
So
You'll hear more impairments than regular.
they're more critical, whereas a naive rater will tend to rate, with a mean of a central tendency bias, a mean of 3.
I think, I think there are a lot of things that I think this kind of experiment will never be really realistic. We try to do as much as we can. One thing that I was thinking is different when you are listening to an audio and when you are having a conversation using Skype service. So then, and if you are paying, the service is even worse. But there you are getting paid to do that. So I think that also might play a
No,
factor.
definitely data is so important, right? There are companies who are just selling data to ITUT and their job is to just collect data for mass evaluation.
Yeah.
And you're doing it for 3 months, it's a good achievement.
Yeah.
Right? We're doing as much as we can, definitely.
So one question, how much cleaning of the data did you do? Like were there any consistency checks? Did you find bad raters and throw them out?
We didn't actually did much of that actually.
We did have spam filter on.
Right.
So if some raters were varying too much time from the mean, so they got spammed out.
Okay.
And that was actually one of the problems. We stopped getting the hits at certain point because most of them got spammed out.
You mean like during the test or after?
It could be post-test as well.
Yeah, the post processing, right?
Yeah.
We didn't have really time for do post processing, but
Okay.
I mean, with the HIS we had to kind of.
Most of them got filtered during the tests.
So that's good.
And we relaxed the spam filter, right? So
Right.
So when you had 10 judges and everybody disagreed on everything, you still calculated the average?
Yeah. You see that I think there's a lot of variability in this data for sure.
Would it help if you then looked at each judge, if each judge was given a low quality sample, a high quality sample, to look at what that judge's range is, and then
We have done this with
Yeah,
emotion
yeah.
detection
Does that make a
algorithm.
difference?
So another thing is like if you check the ITUT recommendation for this test, they say you should start with the conditions that you want to do this experiment. So the conditions should be very clear. People should not have second guess about what they are hearing. But this is not realistic. You're not going to be in an environment with only reverberation or only noise. So that's what I think was the challenge of this data set, to have something realistic, at least on the side of the impairments.
But maybe one consistency check that could be added would be you always ask the same rater, you give them the same file, and you make sure they're rating it the same. If they're off by a huge number,
Okay.
then you know they're not reliable.
Yeah.
One small comment maybe on since you collected what people used to listen to the samples, there might be some interaction between, if they listen over speakers and the speech level is low, then yeah, it just drowns in your environmental noise, whereas the noise level being low or high doesn't have as much of an
Yeah.
effect because it just
That's right, yeah.
So just seeing what
Lots
happens.
of data mining we can do on those
Yeah.
100,000
Yeah.
judgments.
Yeah.
Is there
That
no
might
way
be
to,
interesting to see, just throwing out all the speaker-based ones and see what.
is there no way to buy this kind of data from somewhere?
Just
Like you guys?
We just bought it. Cost us $10,000.
No, what I mean is people would have done this more rigorously, right? I mean, there is this company which does POCA, which develops all this PESC and all that. What is that company's name? It's in Europe somewhere.
Head acoustics.
Head Acoustics.
No, Opticom.
Opticom. Head Acoustics also.
makes the control software, but they don't do this. They sell you the $50,000 or $100,000 equipment to do lab tests.
And they don't sell data.
Opticom will sell you POCA. No one actually sells data to do these things. So,
And you won't know if it is suitable, if that data is suitable for your application.
Right.
Because we got actually the actual Skype pipeline, so whatever they did is very, very Skype relevant.
Yeah, Skype element also.
So more questions?
Can I add a comment close to what you just said? I think all this averaging might be killing the application because you really don't want to average all these opinions if your intended application is for telephone versus quality versus Skype in a conference room quality versus Skype at home quality. So definitely.
Yeah,
what
that's
would be-
something I think Hannes was saying, right?
'cause this-
But then you cannot call it MOS anymore. You have to call it something else, I guess.
But the averaging reduces the noise. in
Yes,
the-
on one hand. On the other hand, do you really get valuable information more tailored to your application? I guess that's the.
I don't know, Ross, because the ITU2, they say should have like 20 people. We got 10. Is enough, 10, like in your experience, like it's kind
Yeah,
of.
but so your deviation of the average is way lower than humans. So technically, presumably you get better results than a bunch of humans. And I just estimated 0.16 mean square error compared to one of a single human is equivalent that this 0.16 is equivalent of tests with 40 humans. One under square root of 1 under n is the number of if they meet the statistics, okay? But that pretty much means that each measurement with this tool is equivalent of MOS with 40 humans.
Okay.
More questions?
I have again one question to this slide where you showed the correlation between SNR and MOS. So that was the correlation between the SNR, how you generated the data. Right?
Yeah, it's the actual.
So it would be would be interesting to see the correlation if you compute the SNR at the output, which also then contains takes the impairment of the processing and all these artifacts and package loss and these things into account. So,
Yeah.
and I would probably expect to be this a much higher correlation.
So SNR is what, the input of the pipeline or the output?
It's the input.
The input.
The input.
So technically, it's actually the SNR is higher because the Skype pipeline cuts 10 each.
But
15
the
each
thing
dB
is-
of noise.
Yeah, but we have like actually 50% of the data is without the pipeline, so you actually could check the difference at least.
Yeah, but in the column of 20 dB SNR are the files with 20 dB input SNR and the files with 20 dB input SNR but processed by the Skype pipeline, which means the output is, let's say, assuming 10 dB SNR improvement, they are actually at the 30 dB vertical. Yes, Sebastian is right. This will, if you measure it exactly there, and that's pretty straightforward actually, it will make the, but still, it's SNR is a poor quality indicator. It's the easiest to obtain, but
That could actually be added to the list of estimators, just SNR as a predictor. But the SNR after the at the output.
It's actually hard to compute real time. I mean, it's easy to compute here.
oh, but because we have the clean speech file, we run the video,
That's
the
right.
clean speech, and then estimate.
But it's not practical to compute in a real system.
Yeah, just as a reference point for
Sure.
Comparison.
One question, so you use a constant 10 samples or 10 ratings per file, but in reality, that should probably be adaptive because different noise levels, different impairment types will require more ratings or less ratings.
Okay.
So the humans are not going to be consistent across all different types of files.
Okay.
So you could use your data to figure out how many samples you need.
Okay. For depending on the impairment.
That's right.
Okay. Yeah, there's a lot of data to play with for a long time.
More questions? If not, let's thank our speaker. Thank you.